When you read a sentence, your brain does not give every word equal importance. You focus on the words that matter most. Transformers do the same thing. They use attention weights to decide which words deserve the spotlight and which can stay in the shadows. Imagine you are at a loud party. 10 people are talking at once, but you can only focus on one conversation. Your brain automatically turns up the volume on the conversation that matters and turns down everything else. Attention weights are that volume knob, a way of telling the model which words to listen to and which to ignore. Every word in a sentence gets a score, a number between 0 and 1, that says how much attention it deserves. The word cat might receive a score of 0.9 when predicting the next word, because cat and sat are closely related. The word the might receive only 0.1 because it carries less predictive meaning. These scores are the currency of attention. All these scores are organized into a grid called the attention weight matrix. Each row is a word asking the question, which other words should I pay attention to? Each column is a potential answer. The brighter the cell, the stronger the connection between two words. This grid is the brain of the transformer, a map of meaning waiting to be read. Every word creates 3 vectors, 3 arrows pointing in different directions through space. The query is what the word is looking for, its question. The key is what the word has to offer, its identity card. The value is the actual meaning the word carries, its payload. These 3 vectors are the raw materials from which attention weights are forged. To calculate the weight, the query from one word is compared against the key from every other word in the sentence. When cat queries, it scans all the keys. The key from sat matches strongly, they belong together in meaning. The key from banana barely registers at all. The strength of this match becomes the attention weight, the model saying yes, these words belong together. The matching is done with a simple math operation called the dot product, the alignment of 2 arrows in space. If they point in the same direction, the score is high, signaling strong attention. If they point in opposite directions, the score is low, signaling weak attention. This single calculation, repeated billions of times, is the heartbeat of modern artificial intelligence. The raw scores are messy numbers that do not add up to anything meaningful, so they are passed through a function called softmax, a magic funnel that turns any set of numbers into clean percentages that sum to exactly 100. Now each word knows precisely what fraction of its attention to give to every other word in the sentence. Finally, the attention weights are used to blend the value vectors together into a single output. Words with high weights contribute more of their meaning to the mix. Words with low weights barely affect the result. The output is a new vector that captures the word's meaning in context, enriched and informed by the words that matter most. Here is why attention weights are so powerful. The word bank means completely different things in different contexts. When bank appears near river, it attends strongly to water and nature words. When bank appears near money, it attends to finance and commerce words. The same word, transformed by attention into entirely different meanings. Old models could only see nearby words, as if reading through a narrow tube. But attention weights connect any 2 words, no matter how far apart they sit in a sentence. In the cat that I saw yesterday in the park sat on the mat, the words cat and sat are connected through a single beam of attention, even though 12 words separate them. This is what gives transformers their remarkable grasp of long sentences. A transformer does not use just one set of attention weights. It uses multiple heads, like having 8 different spotlights, each focusing on different connections in the same sentence. One head might track grammar relationships. Another might track meaning. A third might track who did what to whom. Together, they build a rich, multidimensional understanding of language. When researchers visualize what different heads learn, they find fascinating patterns. Some heads focus on the previous word, a simple local pattern. Others connect adjectives to their nouns across long distances. Some even learn to track quotation marks, bracket pairs, or the relationship between questions and answers. Each head discovers its own linguistic specialty. There is one more elegant trick. The scores before softmax are divided by a temperature number, a single dial that controls how focused the attention becomes. Low temperature makes the weights sharp, almost binary, focusing intensely on just 1 or 2 words. High temperature makes the weights smooth, spreading attention more evenly across many words. In a real transformer, attention happens not once but dozens of times in sequence, stacked like floors in a tall building. Each layer refines the understanding from the previous layer. The first layer detects basic word relationships. The second layer detects phrases and clauses. By the 10th layer, the model understands complex sentence structures and abstract meanings. There is also cross-attention, where words from the output look back at words from the input. In translation, when generating the French word chat, cross-attention connects it strongly to the English word cat. This is how the decoder knows which input words to focus on for each output word. A bridge between two languages, built from attention. Researchers love to visualize attention weights as heat maps, glowing grids where bright spots reveal strong connections and dim regions reveal weak ones. These visualizations expose how the model thinks, which words it considers related, and why. They are like an X-ray of the model's reasoning process, a window into the mind of the machine. Attention weights are not perfect. Sometimes the model attends strongly to common filler words like the, or is that happen frequently but carry little meaning. Researchers call this phenomenon attention sink, a tendency for attention to pool in common, predictable places. It remains an active area of research to make attention more precise and meaningful. Attention weights are how transformers decide what matters. Every word queries every other word. Scores are calculated, and the strongest connections carry the most meaning into the output. Multiple heads look at different patterns. Stacked layers build deeper understanding with each pass. This simple mechanism, scoring how much one word should focus on another, is the engine that powers all modern language understanding.